Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome to another episode of Stories from Space. I'm your host, Matt Williams, and today I wanted to get into a very fascinating topic, and one which is very near and dear to my heart, and it concerns a subject which is vitally important to the search for habitable planets beyond Earth, and of course the search for life in our universe, aka astrobiology, the concept of a circumsolar habitable zone, or habitable zone for short, which is to say the orbit that a planet would need to have around a star in order for life to be able to emerge and thrive there. Now, over the years, with the huge explosion in the number of confirmed exoplanets, this concept has evolved, and part of this has to do with the fact that our very notions of habitability have also evolved thanks to the large sample of exoplanets that we have been able to study thus far. Prior to the Kepler Space Telescope and the thousands of exoplanets it was responsible for detecting, scientists were largely confined to using our solar system as an analog for other star systems, and it was sort of naturally assumed that what we have here is essentially the standard by which habitability in habitable star systems can be measured. But that has changed in recent decades, as I said, because of the sheer number of exoplanets we've discovered. The more exoplanets we can confirm and the more we can learn about them in turn, it influences our very perception of what type of planets are most common in the universe and what conditions are likely to exist on their surfaces. And of course, there's also the fact that scientists have been looking at how life emerged on Earth, and there are a number of important considerations that need to be factored in when we talk about what does it take for life to exist. In the past, the concept of a habitable zone really came down to one thing: the distance that a planet would need to orbit from its star in order to receive enough sunlight and enough warmth that water could exist on the surface in liquid form. However, even by this simple definition, there are a number of caveats that have to be taken into account. For starters, the distance that a planet would need to orbit its star depends entirely upon the star itself, whereas your larger classes of stars, which are typically much hotter and brighter than our sun, for example, their circumsolar habitable zones tend to be much farther out. In addition, they'll have a wider circumsolar habitable zone, which means that more than one planet could in fact fit into this region, whereas your G-type and K-type stars, our sun being an example of a G-type main sequence star, or yellow dwarf, and K-types being orange dwarfs, these tend to have tighter habitable zones, so closer to the star and less wide, less broad. Whereas your smaller red dwarf stars, also known as M-type stars, which are typically much smaller, dimmer, and cooler than other classes, they have rather tight and constrictive habitable zones, so really quite close in, and rather narrow by comparison. So you might think that's pretty straightforward. The bigger, more massive, and hotter the star, the more distant its habitable zone is going to be, and the more extensive it's going to be. But even there's another all-important consideration, which is the age of the star. For example, when dwarf stars first form and their planetary systems have fully accreted and are now orbiting it, They've not yet entered what is known as their main sequence, which is the longest stretch of their lifetimes, in which their color, brightness, and the intensity of the radiation they emit will evolve with time. For example, hundreds of millions of years ago, our sun was actually dimmer than what it is today. Earth received less in the way of solar radiation. So it was necessary for our atmosphere to have higher concentrations of carbon dioxide in order to maintain the kinds of temperatures that were stable over time. And as our sun has gotten brighter, atmospheric carbon dioxide levels have dropped off accordingly. What's more, stars like our sun, they remain within their main sequence phase for about 10 to 11 billion years, whereas much larger, more massive stars have much shorter-lived main sequence phases. And given that our solar system formed roughly 4.6 billion years ago, that means in about 5 billion years, our sun will have run out of hydrogen fuel in its interior, and at this point, it will expand considerably to become a red giant. And scientists currently predict that when our sun does become a red giant, it's going to expand to the point where just about all the inner planets, including Mercury, Venus, Earth, and maybe even Mars, will be consumed, at which point the habitable zone of our solar system will have moved or relocated much farther out. At this point, what is known as the frost line, the boundary in our solar system beyond which volatile elements freeze solid, which is roughly located in the asteroid belt, beyond that will now be the new habitable zone of our solar system. And so you see, even by the simplest definition there, the distance required to maintain liquid water on the surface of a planet, that the concept of a habitable zone, it changes with time, it evolves. And as the example of Earth and its varying levels of carbon dioxide in the atmosphere of its greenhouse gases, the chemistry of a planet's atmosphere also plays a very, very important role in determining or defining what a habitable zone is and what its extent is. And this brings us into another key area of astrobiology, the search for life in our universe, and how that applies to circumsolar habitable zones in the very definition of habitable planets. And it comes down to what is required for life to emerge and to thrive, and for the climate of a planet to remain stable over time. As Earth's own geological history indicates, there will be shifts and changes due to changes in the planet's axial tilt or just the dynamics between the star and the planet itself. Nevertheless, over the long haul, the presence of certain elements are what ensure that life can continue to survive and continue to emerge and evolve. And as we addressed in the previous episode, the search for biosignatures, water is considered foremost among them, because, as we know, all life forms on Earth rely upon water in order to carry out basic functions and to survive. And not only that, but based on the most recent, up-to-date fossilized evidence, it is now known that the earliest life forms, they emerged roughly 4.1 billion years ago, and they did so within Earth's oceans around hydrothermal vents. And this indicates that life emerged almost immediately after Earth had oceans to begin with. And the next most obvious is carbon dioxide, because as we know, Earth's primordial atmosphere, it consisted predominantly of gases released from Earth's interior through volcanic eruptions, so a process known as volcanic outgassing, and the largest component of that was carbon dioxide. And so, over time, this led to the first cyanobacteria and other photosynthetic organisms, which were still single-celled and relatively simple by this time. Nevertheless, these organisms are what allowed for oxygen to be introduced to the atmosphere. By combining water and carbon dioxide with an energy source, in this case, sunlight, they were able to produce glucose as a food source and oxygen gas as a waste product. And over time, this had the effect of drastically transforming our atmosphere, leading to the Great Oxygenation Event. And at first, this triggered mass extinctions there, where much of the organisms that depended upon a carbon dioxide atmosphere began to die off. But of course, that led to eventually an equilibrium being achieved, where oxygen-consuming organisms emerged. And this led to the first complex life forms that were not only multicelled and had mitochondrial DNA, but were much larger and had complex systems of organs in order to metabolize oxygen and nutrients. So naturally, oxygen is also considered a biosignature. And since nitrogen plays such an important role through the nitrogen cycle in the lives of plants and trees and other foliage that are essential to maintaining the balance of carbon dioxide and oxygen in our atmosphere, nitrogen is also considered a biosignature, not only in the form of nitrogen gas, which acts as an important buffer in our atmosphere between oxygen, CO2, and other trace gases, but also in the form of ammonia, as ammonia is a natural solvent, much like water, predominantly composed of nitrogen, and the nitrogen byproducts like nitrites and nitrates are essential for plants as a food source, and it enriches the soil. So ammonia is there too. And last, but hardly least, there is methane. Methane is yet another solvent that is found naturally occurring in nature. It's made up of hydrocarbons, which is why it is combustible and flammable. But those hydrocarbons are key to life. Carbohydrates themselves are a main source of food energy for complex animals like humans. And those essentially consist of long chains of hydrogen bonded with carbon and oxygen. And when organic matter dies and begins to decompose, methane is what is released. And it is in some organisms also a byproduct of their digestion process, such as cows. And as I'm sure our listeners know, it plays a rather important role in the dynamics of our atmosphere because methane is a super greenhouse gas, as is ammonia. So these two are not only essential to organic life as we know it, they also help maintain the atmospheric balance and stable temperatures over time on a planet. And so, when looking at how planet Earth itself has evolved over time, how its atmosphere has changed, how its dynamics have ultimately led to the emergence of life, and how the presence of life itself changed the way the planet works, these are all rather complex considerations that scientists need to take into account when attempting to determine if a planet is potentially habitable or not. As recent studies have shown, planets that orbit red dwarf suns, they are particularly good at forming systems of rocky planets. In fact, within 50 light years of our solar system, we have identified a total of 30 star systems where potentially habitable rocky planets reside, and of those, 29 are red dwarf suns. And these planets, many of which were super Earths, but several were comparable in size to Earth too, they tended to orbit within the circumsolar habitable zone, so just the right distance from their sun that they would get enough heat to maintain liquid water. But because, as I said earlier, red dwarfs have a rather up-close and tightly constricted habitable zone, that means that these planets orbit very close to their stars, and as a result of that, the gravitational pull of the star, it has led to a situation known as tidal locking. And what this means is that the planet's rotation has become synchronized with its orbit around the star, so that one side is constantly facing the star, and the other is dealing with perpetual darkness. And along the terminator, or the boundary between the sun-facing side and the dark side, you have perpetual twilight. And this is very much the situation we have here on Earth with the moon. The moon is tidally locked to us, which is why we always look up and see the same face, and why we talk about the dark side of the moon, or rather the far side, because it still gets plenty of illumination from the sun. It's only dark in the sense that we don't see what's there at any given time. What's more, scientists have noted from spectral observations of these systems that they appear to have a lot of water, and this is evidenced by the loss of hydrogen to space, what's known as atmospheric escape. When you have water on the surface of a planet that's bombarded by solar radiation, the hydrogen and oxygen atoms of water, they chemically disassociate. And whereas the oxygen gas created from this process will be retained by the planet, the hydrogen gas is lost to space. And so from this, scientists have theorized that there may be many red dwarf planets out there that have plenty of oxygen in their atmosphere. But this does not necessarily make them habitable, because not only was this oxygen created through inorganic processes, so it's known as abiotic oxygen, but using Earth as a template again, life would have an incredibly hard time emerging on this planet because the presence of an oxygen atmosphere would be toxic for simple organisms. It was only through the transition of carbon dioxide to an oxygen-rich atmosphere that simple organisms gave rise to more complex organisms that use oxygen as a fuel source. And so this has led to a term known as transiently habitable, where a planet could be habitable to life as we know it now, as it has come to evolve. So we could seed planets with our own life and they would be able to thrive there. Life in the indigenous sense would not emerge on its own, at least as we know it. And this is seen as particularly likely around red dwarf suns because they are very long-lived, whereas our sun and similar G-type or K-type dwarfs tend to live for about 10 billion years before they leave their main sequence. It is estimated that red dwarfs can remain in their main sequence for hundreds of billions of years, even trillions. And a consequence of that is that they take a while to get into their main sequence phase. So in fact, what is their habitable zone once they are in their main sequence is not what their habitable zone was before that. And so planets that are located in what will become a red dwarf's Goldilocks zone, another term used for it, would be subject to a lot of radiation from this newly formed red dwarf star for billions of years. And this could have the effect of turning water that is on their surface into abiotic oxygen, and thus creating a world that would be hospitable to advanced life, but very hostile to emergent life, at least as we are familiar with it. And, as also mentioned earlier, Earth's primordial atmosphere was the result of volcanic outgassing. And a look at the geological record shows that plate tectonics have played a pretty vital role in the evolution of life. In fact, scientists believe that the Cambrian explosion, as it's referred to, which took place roughly 530 million years ago, this was characterized by a wide variety of animal species. The majority of the taxonomies that we are familiar with today, they suddenly, quote-unquote, appeared in the fossil record. Now, of course, this happened over the course of many millions of years, but it is referred to as an explosion, and the term sudden is used in the sense that this seemed like a very brief period of time for such an explosion to happen. And, of course, subsequent research since the late 19th century, when this Cambrian explosion was first identified in the fossil record, it has shown that there was actually a lead up to this. It wasn't an explosion so much as a faster than normal rate of evolution for terrestrial species. Nevertheless, the latest explanation as for why this explosion took place when it did, which is certainly the most comprehensive explanation offered to date because it manages to synthesize several other theories, has to do with a slight increase in oxygen levels that occurred during the same period, as well as the existence of shallower marine environments, which led to more oxygenated waters, and this coincided with the breakup of the Pannotia supercontinent. So in essence, the movement of tectonic plates, the breakup of the supercontinent to form all these shallower oceans and new niche environments between the new continents that existed by the Cambrian period. This is what allowed for rapid evolution and diversification of life, on a geological timescale at least. What's more, tectonic activity plays a very key role in the maintenance of Earth's carbon cycle. Carbon is sequestered into the Earth repeatedly by the convection of the mantle plate, and this is what results in the formation of carbonous rocks in the interior, which store carbon dioxide in them. And carbon dioxide is then released again into the atmosphere through volcanic activity. So again, the presence of plate tectonics and the planet being geologically active would seem to play a very key role in the evolution of life and its eventual diversification, complexity, and as well the maintenance of a stable environment that can host it. And interestingly, this is something that is unique within our solar system to Earth. Earth alone appears to have tectonic plates with sharp boundaries that are constantly moving and shuffling, whereas the Moon, Mercury, Venus, and Mars all appear to have just one plate, which covers the entire surface. There are no boundaries, no breakups, no movement. So this is what's known as a stagnant lid planet. But, interestingly, Venus and Mars are not also geologically dead in that respect. There is evidence that Venus experiences volcanic activity on its surface semi-regularly, and that Mars itself still has magma in its interior, and that there's still heat in the movement of lava beneath its surface. And so far, scientists are unsure whether or not this would apply to exoplanets as well. There is research that considers super-Earths and indicates that they are likely to not have tectonic activity, that they are most likely stagnant lid worlds, but this remains to be seen and tested. All that we can say at this point is that the presence of tectonic plates and their movement as part of a geologically active world is vital to life as we know it, and certainly has been here on Earth. And what is especially interesting is that tectonic activity does seem to take place in icy bodies in the outer solar system. And we're talking Europa, Ganymede, Triton, and evidence of plate movements were observed by the New Horizons probe on Pluto. However, rather than it consisting of a sheet of rock and silicate minerals, this tectonic movement was ice sheets, either composed predominantly of water ice with other volatiles mixed in, or nitrogen ice in the case of Triton and Pluto. And that is quite similar to cryovolcanism. It is a type of geological activity involving the movement of material in the interior that is liquid due to tidal flexing, much like lava, but instead we see water, and it is spewing out of mountainous features that are made of ice and other volatiles instead of rock. And this brings us to yet another consideration when defining things like habitable zones. If, in fact, the outer solar system is full of ocean worlds, and it certainly is, and if, in fact, these can host life in their interior, does that not mean that the habitable zone as we know it is far too constrictive, that beyond the frost line of any solar system, icy moons that orbit gas giants and have all the necessary components there, tidal flexing in their interiors, the exchange of the material between the surface and the interior, liquid water, hydrothermal vents, and the necessary chemical elements for life, as well as an energy source, which can take the form of heat provided by the hydrothermal vents, as well as the decay of radioactive elements in the rocky and metallic cores of these worlds, then is it not a safe assumption that life can exist well beyond the boundary where water can exist in liquid form on its surface? And should astrobiologists therefore consider gas giants that orbit beyond the so-called habitable zone to be a potential abode for life, provided they have exomoons? So, as you can see, our very concept of what constitutes a habitable zone, or a habitable planet, the very notion of habitability, for that matter, it has evolved with time thanks to a lot of new discoveries, new research, And these have come to challenge the traditional notion that the solar system is the archetype or the predominant model for judging what it takes for a planet to host life. We are reconsidering the possibility that water and oxygen themselves are guarantees that life would exist. We're also reconsidering whether or not terrestrial planets are the only place where life could exist. And of course, we're taking into account the evolution of stars and planets themselves, and how the presence of life itself is responsible for altering the environment in such a way that habitability is extended and more life can exist. So in that respect, having the necessary chemical ingredients that we associate with life today is not nearly as important as having the necessary ingredients for life to emerge in the first place and do its thing and ultimately transform a planet into something that we would recognize today as being habitable. And so, in this respect, astrobiology is just like the search for extraterrestrial intelligence, or SETI, in that it all comes down to the framework within which we're operating. It's limited by our current knowledge, our current examples, and of course, like SETI, that's bound to change in the coming years. Not only has the explosion in exoplanet discoveries and the presence of many space telescopes that are highly adept at finding and characterizing exoplanets, not only are they presenting us with many, many, many more examples of what is out there and what life would have to deal with, at the same time, our exploration of the solar system, which is going to involve a few very interesting missions sent out to the outer solar system in the coming years. And that includes the Europa Clipper mission, the European Space Agency's Jupiter Icy Moons Explorer, or JUICE, which is already launched, and the Dragonfly mission to Titan, as well as a possible Enceladus orbiter and a Europa lander. All of these missions are going to be tasked with picking up where previous missions left off and looking for evidence of life and biosignatures on the surface of these bodies, and as well as of their interior oceans, sampling them to see if there are the necessary ingredients of life, or indeed indications that life could be down there. And what we learn from these future missions and from our next generation telescopes, such as the James Webb Space Telescope, that's already in operation and revealing some wonderful things, which will be followed as well by the Nancy Grace Roman Space Telescope, Hubble's direct successor, the European Space Agency's Planetary Transits and Oscillation of Stars mission, otherwise known as PLATO, as well as the ESA's Atmospheric Remote Sensing Infrared Exoplanet Large Survey mission, aka Ariel. All of these missions are going to teach us about the possibilities and potential for life, not only within exoplanet systems, but also within our own solar system. So in the coming years, we'll be able to search for life, both at home and abroad, and what we find, it'll be complementary, of course. If we find that life can, in fact, exist within icy moons orbiting gas giants, this knowledge will go a long way towards informing exoplanet and exomoon studies, and will also mean that rogue planets, rogue gas giants that have carried along their systems of satellites, that they too could be transporting life as they drift through the interstellar medium. So this will have tremendous implications for astrobiology, but also for what we consider to be habitability and where life can be found. And depending on what we find, we may learn that Earth is in fact a very type of rare environment, very rare jewel, and that life can only exist under very, very tight and constrained conditions, the kind that we only find so far here on planet Earth, or that life takes many forms, that it's ubiquitous in the universe. And this in turn could have implications for SETI. We may learn that intelligent life is a lot more common than we thought, just not in forms that we would immediately recognize as such, or that while intelligent life may be rare, the product of long, long phases of evolution stretching out billions of years, that basic life could be absolutely plentiful. So, as I often say at the end of these episodes, exciting times lie ahead. And be sure to tune in again, as upcoming episodes will be dealing with Aztec astronomy as part of our ongoing segment on indigenous astronomy, as well as the final proposed resolution of the Fermi paradox in our series known as the SETI paradox. We'll also look at the emerging Chinese space program and what it has in store for us in the near future, as well as India's. And we'll be taking a look at other commercial space companies that are giving SpaceX a run for its money, are pushing the envelope on innovation, and working towards making space accessible for all people. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.